All right, so chapter 3, we go into categorical data. So what is categorical data? Categorical data is data that is in counts. Okay? And it is without units. So for instance, if we were counting the number of 9th graders, 10th graders, 11th graders, or 12th graders, that would be categorical data. We're taking people and putting them into categories. So this is a form of a contingency table. The table is contingent upon whether people, what their favorite football team is. So when looking at a single variable or a single group, we can keep our data in counts. So a bar graph is fine. So in this case, we would do we would just do up to 80, and we would do the Giants would be 60, and the Jets would be 60, and the Patriots would be 80. Okay, so that's very simple. Now if we wanted to change this to percents, we could do a pie chart or a relative frequency bar chart. And all that term relative frequency really means is change it to percentages. So we're going to put everything in percentages. So we have 200 people. 60 of the 200 are Giants fans, that's 30%. 30% are Jets fans, and 40% are Patriot fans. So we make a nice little circle. So I'm going to do about 60%, divide that in half. That's 30% Giants fans, 30% Jet fans, and 40% Patriot fans. Okay. We probably should have labels here, so this would be people. And this graph would be a graph of a favorite football team. And this graph would be titled Favorite Football Team. And then this last one, we would just do a bar graph in percentages. So our highest is 40%. So this is percent of people. And this is favorite football team. And what do we got here? We got that's the Patriots are 40, right? And then the Jets are 30, and then the Giants are also 30. So that was just a relative frequency bar chart. I just put them in a different order, but so these are really the same kind of representations in that they're using percentages, but one's a pie chart and one uses bars. Alright, so comparing variables across categories. When we compare two or more variables across several categories, we use a contingency table. As shown below. Okay? So in this case, we have the 60 Giants fans are 30 males and 30 females. The 60 Jets fans are 50 males and 10 females. And the 80 Patriots fans are 20 males and 60 females. That gives us our 200, 100 males, 100 females. So unless the counts are the same, we have to use percentages to compare. Okay? So and statements. The probability on and statements are limited to a variable in a category. They were always out of the total. So the probability of male and Giants fans. Well, there are 30 males and there are 200 total. So it's 30 out of 200. So that's 15%. Female and Jets fans. Well, that's 10 out of the 200. Marginal distributions are distributions that are in the margins. Okay? So marginal distributions use totals. In the case above, the marginal distributions were by gender and football team. So, we have the same, now these are the margins, 60, 60, 80, and then 100 and 100 is 200. So the probability of being a Giants fan, well, here's your Giants fans. That's 60 out of 200. Probability of being male, well, there's 100 males, 100 out of 200. Probability of being female, there's your females, 100 out of 200. Probability of being a Jets fan, 60 out of 200. Conditional distributions narrow the category that we look at. So when we start looking at conditional distributions, now this starts to, these do not use totals, okay? So if we look at gender, there's 100 of each. Now the probability of a Giants fan given that they're male, well, the given that, that's the group that we look at. So we have 100 males. Out of those 100 males, how many of them are Giants fans? Well, 30 of them are. So it's 30 out of 100. Probability of a Pats fan given that they're female. Well, how many females are there? There's 100. How many of the females are Patriots fans? 60 of them. So it's 60 out of 100. Now we do it by team. So we have 60 Giants, 60 Jets, and 80 Patriots. Female given that she is a Jets fan. So we're looking at Jets fans. There are 60. How many of them are female? 10. So it's 10 out of 60. Male given that it's a Pats fan. So we're looking at Patriots fans. There are 80 of those. Of those 80 Patriot fans, how many of those are male? 20 of them. Alright, so now we're looking at the graphical displays. So now we want to look at the distribution across gender. So there are several graphical displays, such as pie charts or relative frequency bar charts. But when comparing two categorical distributions, we will generally use a segmented bar chart. And the reason you're going to see is it's very easy to compare the distributions. So let's just take our last page here, and we have this is our gender. So if I look at males, there's 100 males. So 30 out of 100 is 30% are Giants fans, 50% are Jets fans, and 20% are Patriot fans. For females, 30% of them are Giants fans, 10% of them are Jets fans, and 60% of them are Patriot fans. Okay? So now we draw what we call a segmented bar chart. So we're comparing males to females. And a segmented bar chart always goes up to 100%. Okay? And I'm going to start with the males. Okay, so our males, it says we need 30% Giant fans. So here we are, we're going to put 30% Giant fans. And then 50% of them are Jet fans. So 30% plus 50% is 80%. So I'm going to put 80% Jet fans. Sorry, 50% Jet fans. It goes up to 80%. So 30 plus 50 brings me up to 80, and then the last 20% are Pats fans. So 20% Patriot fans. Okay? Now we do our females. Well, our females are 30 Giants, 10 Jets, 60 Patriots. So we draw. So 30% Giants, 10%, so 30 plus 10 is 40, so that brings me here. So it's 10% Jets fans and 60% Patriots fans. Okay? So, are the distributions roughly the same? Well, no, they're not. While Giants fans are equal, more females like Patriots fans, and half the males tend to like Jet fans, so the distributions are not the same. So let's talk about independence. When two variables are independent, then the categorical distribution across variables is roughly equal. If they are not equal, then there is an association. Well, is our distribution equal? Well, no, it's not, then there's an association. So let's look at our example. Are the distributions across genders the same? No. The majority of females like Patriots fans and half of the males like Jets fans, so they're not the same. If so, then the variables are independent. Well, they're not independent. If not, then there's an association. The association in this case is the majority, 60% of females are Pats fans, while half of the males are Jets fans. So, males tend to like the Jets, and females tend to like the Patriots. Alright, so the area principle. Graphical displays must be made in good form, and the most common problem with graphical displays are: number one, violation of the area principle. This is most common with 3D graphics. So, for instance, somebody draws a graph, a pie graph, with 50%, so it's supposed to be a 50% region, and the region that's shown is not 50%. It's a violation of the area principle. Okay. Not putting a title. Okay. The graph is made for people to read it. Well, if people don't know what it's saying, then, or what it's about, then the graph is useless. Insufficient or not labeling categories in a graphical display. So we look at the first one. Well, we have a violation of the area principle. We don't know, because we don't know what these percentages are. So there's a problem with labeling. Should have the percentages in there, and there's no title. The second one, again, this is about crew, first class, second class, third class. Well, there should be a title. It's probably about a boat. But then these are in counts. Pie charts are never in counts. So these should be in percents. If you're going to use counts, you use a bar graph. And then the last one is a violation of the area principle. This 50% is not 50%. Okay. This 26.7%, that's close, but it should be over a quarter. It doesn't look to me like it's over a quarter. It looks like to me like it's just short of a quarter. And there's no title. So those are the pitfalls to watch when you are doing graphs for other people to use. Alright, so let's look at what's called Simpson's paradox. So in this we have, it's the last inning of a game, and we have 2 outs, the bases loaded. So we get to send in a pinch hitter. So we have player A who's 33 for 103. So if we do 33 divided by 103, we get 0.320. And player B is 45 out of 151. So if we divide those, we get 0.298.
So compare A's batting average to B's. Which player appears to be a better choice? Well, player A has a higher batting average. So we would probably choose player A. So we should send player A into the game. Well, now we take apart A's at-bats. So A we know is a 320 hitter, and B we know is a 298 hitter. But let's see, player A versus left-handers, 28 divided by 81 is 0.346. And then 5 divided by 22 is 0.227. So it looks like A is a really good hitter against left-handers, but not against right-handers. And then player B was 12 for 32 versus left-handed pitchers, so that's 0.375. And 33 for 119 is 277. So look, player A has the higher batting average, but player B has the higher batting average versus left-handers and right-handers. Which player appears to be the better choice now? Well, player B has a higher batting average versus both left-handed pitching and right-handed pitching. So we should send up player B. Okay. Well, why did this happen? Well, let's look at the left-handed pitchers. Well, it looks like player A got most of their at-bats versus left-handers. They got 81 attempts versus left-handers and only 22 against right-handers. Okay. And B got most of their attempts against right-handers and not many against left-handers. So you notice how their averages are both higher versus left-handers and lower versus right-hander. So left-handed pitcher was easier to hit. Right-handed pitcher was harder to hit. There's a reason in baseball. Righties don't like batting against righties and lefties don't like batting against lefties, but righties like batting against lefties, and I'm not going to go into it. But so what happened is player A got most of their at-bat versus the easier pitcher to hit, and player B got most of their at-bats versus the harder pitcher to hit. But player B still had a higher average versus both types of pitchers, but because they had most of their their attempts versus the harder pitcher, their overall batting average was lower. Because player A had most of their attempts versus easier pitching, their overall batting average was higher. Okay, so the reason was that player A had most attempts versus left-handed pitching, while player B had most attempts versus right-handed pitching. Okay. So what is this? This is known as Simpson's paradox. Simpson's paradox. So these in here are the categorical distributions, and this here is the marginal distribution. So a lot of times we want to think just because the marginal distributions are higher, the categorical distributions will be higher, but that's not necessarily the case. And in this case, especially when there's inequities in the categorical distributions, when one of the groups is doing something harder than the other, then what happens is the categorical distributions tell a different story than the marginal distribution does. That's known as Simpson's paradox.